This is Math 105, Section 3.7. We're going to start by talking about rational functions. Okay, so rational function has this form. R of x equals p of x over qx, where p of x and q of x are polynomials. So we have basically a ratio of polynomials, right? P of x over q of x. Okay, and we assume that p of x and q of x have no factor in common. In other words, if we have common factors, we'd cross them off. We'd simplify the fraction. Okay. Their graphs look quite different from our graphs of polynomial functions. They're not necessarily, in fact, they generally aren't smooth curves. Okay, when we talk about the domain of a rational function, that's all the real numbers except where the denominator is 0. So we'll always check the denominator and see where it's equal to 0, and we'll exclude that from our domain. Okay. So when we're graphing a rational function, we also must pay special attention to the behavior of the graph near those x values where it's undefined. Okay, because it doesn't, have defined points at that point. So nearby, it's going to do strange things with the curve. Okay. Okay, let's start with the function f of x equals 1 over x. That's kind of our simplest rational function, where our p of x is 1 and our q of x is just x. Okay. This function f is not defined for x equals 0 because we can't have 0 in the denominator. Okay. And when x is close to 0, the value of the absolute value of f of x is large. Okay. And the closer x gets to 0, the larger that absolute value gets. Okay, and we can see that down here. First of all, for positive x is near 0, you can see when it's 0.1 for x, our f of x is 10. When it's 0.01 for x, or 1 over 100, remember we're taking the reciprocal, that's what this is a reciprocal function. So that f of x y becomes 100, and if it's 0.00000001, then our f of x is 100,000. So the closer we get to 0, the higher our y is. Okay, and on the negative side, the same thing happens, but our y becomes a large negative. Okay, so if it's minus 0.1 for x, we get minus 10 for f of x. If it's minus 0.01 for x, we get minus 100 for f of x. And if it's minus 0.000001 for x, we get minus 100,000 for f of x. So as we, this is our end behavior, right? Sort of. As x approaches 0 from the negative side, that's what this means, okay? Then y is approaching minus infinity. And as x approaches 0 from the positive side, that 0 plus means from the positive side, then y approaches plus infinity. Okay, so when we're describing the behavior of a horizontal asymptote, we can say our first table, we show that as x approaches 0 from the left, then the values of y decrease without bound. Okay. Another way to say that is as x approaches 0 negative, 0 minus, that means as x approaches 0 from the left. Okay, so that minus after the 0 means we're approaching 0 from the left, which means we're doing this kind of thing with our graph. We're looking at what's happening. Now it's going to minus infinity, but we're seeing what is as, let me redo that little piece there. We're saying what does our graph do as x approaches 0, here's x equals 0 is a y-axis, from the left. Okay, and we can see y is going down, it's going to minus infinity. So we're going along the x-axis towards 0 from the left-hand side. Okay, that's what it means. That's what x arrow 0 negative means. That means we're approaching 0 from the left-hand side. And what happens when that's going on? Well, our y, or f of x, is approaching minus infinity. So we're saying y approaches negative infinity as x approaches 0 from the left. Okay, so that's the symbols for that. Okay, y approaches negative infinity as x approaches 0 from the left-hand side. Okay, our second table shows that as x approaches 0 from the right, the values of f of x increase without bound. Okay, in other words, as x approaches 0 positive, y, or f of x, approaches positive infinity. Okay. Okay, so that would be this symbol. As y approaches infinity, f of x approaches infinity, as x approaches 0 from the right, and we see x approaches 0 positive. Okay, so again, getting back to our little graph of 1 over x, we have, show the two parts there. Okay. As we go on our x towards 0 from the right-hand side, our y is going up to infinity. Okay, so as we go this way on our graph, we're going towards 0 from the right-hand side. X approaches 0 from the positive side. Okay, that's what that 0 plus means. Our y is going up to infinity. And we see as x approaches 0 from the negative side, our y is going down to minus infinity. Okay. And then our next two tables, we're going to look at larger values of x, positive or negative. So the next two tables will show how f of x changes as absolute value of x becomes large. You know, we're taking large positives or large negatives. So here we're approaching minus infinity for x. And notice our f of x gets really close to 0. We can see that when x is minus 10, our y is minus 1/10 or minus 0.1. When x is minus 100, our y is minus 0.01 or minus 1/100th. Okay. And when x is minus 100,000, getting larger and larger negative, our y is getting closer to 0. Now it's minus 1 over 100,000 or minus 0.000001. Okay. And then the same thing happens for the positive, but it gives us a positive y. So a positive 10x or positive 10 for x would give us a 1/10 for y. 100x would give us 1/100th or 0.01 for y, and 100,000 for x would give us 0.000001 or 1 over 100,000 for y. So we can see as x gets bigger, larger, negative, the y becomes closer to 0, right? As y is approaching 0, or kind of looking backwards, as y approaches 0 from the negative side, x approaches negative infinity. See that? And here we can say as y approaches 0 from the positive side, okay, that x approaches plus infinity. We can see here this thing's approaching minus infinity, this thing's approaching 0, okay, this thing's approaching 0 from the negative side. So let's actually write the little negative there so we can see it's approaching 0 from the negative side. That should be negative there. Okay, and then this one is approaching 0 from the positive side. Okay, so see, and then this is approaching, this x is approaching infinity, and this x is approaching minus infinity. So we can see from those tables that as absolute value of x becomes large, the value of f of x gets closer and closer to 0. Okay, so we can say f of x approaches 0 as x approaches minus infinity, and f of x approaches 0 as x approaches plus infinity. Okay, so we can see, you know, on our table that as x approaches plus infinity, see our y is going down to 0, but doesn't hit it. And then as x approaches minus infinity out here, our y is going up to 0, right? It's negative and it gets closer and closer to 0, but doesn't hit it. Okay, so we can see that that's our horizontal asymptote. That's what's happening out here, right? Okay, and some of the other values of the function at 1 over x, f of x equals 1 over x, is like when x is minus 2, y is minus 1/2. When x is minus 1, y is minus 1. When x is a minus 1/2, y is minus 2. And then for the positives, we'll get positives. So 1/2 gives us 2, 1 gives us 1, and 2 gives us 1/2 for x and y respectively. Okay, so we can say the function f is defined for all values of x other than 0. Okay, so the domain is x, set of all x such that x is not equal to 0. Okay, and then from the graph, we'll see that the range is the set of all y such that y is not equal to 0. Okay, so we would have to observe that from the graph or find the inverse function. And here's our graph of that function. We can see, first of all, when you get x close to 0 from the positive side, you can see y going to positive infinity. And as x goes close to 0 from the negative side, that would be to the left of 0, that our y goes to minus infinity. Okay. And then we also see that you know, the domain is x is not equal to 0. You can see as you walk along the x-axis, it's undefined at the y-axis, which is where x equals 0. And then the range, you walk up the y-axis, and you can see it's undefined at y is not equal to 0, which is the x-axis. So that's how we find the range there. Okay. So that line x equals 0, which is the y-intercept, is called a vertical asymptote of the graph. Okay. And the line y equal to 0 is called a horizontal asymptote. Okay. And just to describe that, an asymptote of the function is a line where the graph of the function gets closer and closer as one travels along that line. Okay, so if you think about, like, first of all, the vertical asymptote is this line. What's happening is the graph is approaching that line, going down this way and going up this way. The graph gets really close to this vertical line, but it doesn't touch it. Okay, and then the horizontal asymptote, y equals 0, which is the x-axis. This is also an asymptote, which you can see the graph gets close to that x-axis as we go this way. X approaches infinity, and it gets close to the line as x approaches minus infinity. So that would be our horizontal asymptote. Never touches it, but it gets closer and closer as we go this way or this way. Okay, and then the vertical gets closer and closer to the graph gets closer and closer to the line as we go this way or this way. Okay, so the formal definition of a vertical asymptote: the line x equals a is a vertical asymptote if y approaches plus or minus infinity as x approaches a from the right or left. Okay, so y goes to plus or minus infinity as x approaches some number, which is where that vertical asymptote is. Okay, so here we have y approaches infinity as x approaches a from the positive side. Sorry, from the negative, from the positive side. Okay, so as x approaches a from the positive side, y approaches infinity. Okay, and here we have y approaches infinity as x approaches a from the negative side. So here's a, and then it's going up. Y is approaching plus infinity as we get close to a from the left, which is the negative side. Okay, and then here we have, for vertical asymptote, we have y approaches minus infinity as x approaches a from the positive side. So from the right-hand side, you can see the graph approaches that line. Okay, and then y approaches minus infinity here as x approaches a from the negative side. So these are all different possibilities of our vertical asymptotes. Okay, a horizontal asymptote is a line y equals some constant b. Okay, if y approaches b as x approaches plus or minus infinity. So we just switch the roles of the variables. Okay. Now, in this case, we have y approaches b, here's b, okay, the dotted line, as x approaches positive infinity. And here we have y approaches b as x approaches negative infinity. So we're going x this way, and you can see that our y is getting down to that b. It will never hit the b. Okay. Now, there's a difference here. When you have a vertical asymptote, you can never cross it. It's where the function is undefined. You can't have the graph there. But you can cross a horizontal asymptote. Okay, not way out here, but in between you can cross it. Okay, so horizontal asymptotes you can cross, vertical asymptotes you cannot. Okay, so we can say a rational function has vertical asymptotes where the function is undefined. Okay, so that's the first case. Where the denominator is 0. Okay, let's look at a rational function of this form. R of x equals ax plus b over cx plus d. Basically, that's this. That's a linear polynomial over another linear polynomial, degree 1 over degree 1. So, mx plus b, right? So that would be some linear over some linear. Okay, these can always be graphed by shifting, stretching, or reflecting the graph of 1 over x, which you just did, right? So we go back to that one with the two curves, right? Here's our 1 over x. Looks like this, right? Okay. Sorry, I didn't do that very clearly, but it's that curve that goes like that, right? Okay. So we can take our 1 over x and shift it, stretch it, reflect it to get anything that's a linear over linear. Okay, let's start with our first example. R of x equals 2 over x minus 3. Okay, so this is linear, right? Because this would be y equals 2 is a horizontal line. This would be a linear as well. Okay, so we start with 1 over x. Okay, and then we can use r in terms of this f of x equals 1 over x by doing this. First of all, we factor out the 2. okay? Because if you factor out the 2, then you have 2 times 1 over x minus 3. Okay, and when we do that, you have 2 parts to it now, okay? You have 1 over x minus 3, which is just 1 over x, shifting that 3 to the right, okay? Because we're taking 1 over x and changing it to 1 over x minus 3. So if you take 1 over x and shift it 3 to the right, you take care of this part. And then this says times 2, you just stretch your y by 2. You're doubling your y values, okay? So you're basically just doing two changes to 1 over x. Okay, so I penciled in the 1 over x. So this is your 1 over x, right? Okay. And what you would do is you shift it 3 to the right. Now that changes your vertical asymptote from x equals 0 to x equals 3, okay? So that would move over here, and then these graphs get shifted. Now I also did this. I also stretched. So I doubled my y value. So the y, you can't quite see it here, but if you double the y values, that takes care of the 2 part. So you're shifting the 1 over x to the 3 to the right, and then stretching your y's, okay, pulling them up and down on the ends, down, pulling these ends and then pulling these ends because you're doubling your y's, okay. Same basic shape though, all right. And then we have a vertical asymptote at x equals 3, and then a horizontal asymptote is still at y equals 0, right? So, so our domain is set of all x such that x is not equal to 3, okay, and our range is set of all y that y is not equal to 0. Okay, you can see where y is undefined and where x is undefined. Okay, now for our second example, we have s of x equals 3x plus 5 over x plus 2. This is a linear over linear. Now we can't do quite what we did before with the other graph because we have to do another step first. We actually have to do division here. So we're going to take 3x plus 5 and divide it by x plus 2 using our polynomial long division. Okay, and when we do that, we get s of x equals 3. That would be our quotient minus the remainder over x plus 2, our divisor. Okay, so if we do the division, we're going to get this. Remember the quotient plus remainder is minus 1 over your divisor. Okay, now we can turn this into a graph starting with 1 over x. Basically, if we start with 1 over x, okay, we would have this, okay, and then we go to 1 over x plus 2, okay, and then we go to minus 1 over x plus 2, okay. And then we go to minus 1 over x plus 2 plus 3, okay. Now let's talk about what each of these steps does, right? So starting with 1 over x, we got that graph, right? This shifts it 2 to the right, okay, so that's a 2 to the right shift. Then we're changing our y to the opposite, so we reflect across the x-axis. Okay. Then our last step is just take that graph and add 3, so we move it up 3. Okay, so you can kind of deconstruct the steps once you do this division, right? This is a vertical shift plus 3. We do that last, and then we figure out how we go from 1 over x to this thing, which is what we do that, right? 1 over x to 1 over x plus 2 to minus 1 over x plus 2, and then add the 3. Okay, so we're doing an extra step there. That vertical shift as well. So basically what we're doing is we're starting with our 1 over x. We're going to shift it to the left. Okay, so we're going to have this. There's our 2, minus 2. So we shift it to the left. Okay, minus 2 there. Okay, this is an asymptote, horizontal asymptote. So it goes like that. Okay, and then we reflect it across the x-axis. So I'll do this in red, so we're going to get this one when we reflect across the x-axis. Okay, we get this instead. Sorry. Okay, so now we have this red graph, which is 1 over x, x plus 2, negative 1 over x plus 2 is the red one. Okay, and then we shift it up 3, so that's how we get this red one. Okay, so first step, start with 1 over x, shift it 2 to the left. That gives us 1 over x plus 2. Right, and then minus 1 over x plus 2 is the red, okay, and then minus 1 over x plus 2 plus 3 is this red, okay. So we shifted up that red up 3 to get this red, okay. So that's how we get that. We can see our domain is x is not equal to 2, okay. Vertical asymptote, okay. So S has vertical asymptote x equals minus 2, and the horizontal asymptote is y equals 3, okay. Okay, and then as we said, our domain is set of all x such that x is not equal to minus 2, and our range is set of all y such that y is not equal to 3. And those are our, correspond to our asymptotes that we showed on the graph. Okay, and then to graph more complicated rational functions, we're going to take a closer look at the behavior of a rational function near its vertical and horizontal asymptotes. Okay, in particular, let's look at horizontal asymptotes. Let's not worry about the second paragraph here, but if we're looking at horizontal asymptotes, we're kind of thinking about end behavior, because it's really what's happening as x approaches plus infinity, okay, and x approaches minus infinity. Okay, and that's our end behavior, right? Well, when we're going way out there, we can just look at the leading coefficients in each of the parts of this rational function. So we can look at the leading coefficient of the top divided by leading coefficient of the bottom, and then make x really large, positive or negative, and that will help us determine if we have a horizontal asymptote. Okay, so think of when we talk about horizontal asymptotes, think of end behavior. X is getting really big, and just look at the ratio of the leading coefficients for your top and your bottom. Okay, so that's kind of a simple way to determine your horizontal asymptotes. Remember, vertical asymptotes are just where the function's undefined, where your denominator is equal to 0, but horizontal asymptotes is more like end behavior. So when we talk about horizontal asymptotes, this is our ratio of polynomials, right? We're looking at kind of just the first term over the first term, okay? And think about what happens. If the degree here is lower than the degree here, then we might have something like, let's say we have something like this. I'll put an example to the right here. For the case 2a, let's say we have 3x squared over 5x cubed, right? See, what's happening here is the degree is lower here than it is here. Now, if you make x really large, see, this reduces to 3 over 5x, right? Because we can divide x squared on both the top and the bottom, okay? And when you make x really big, which is positive or negative, positive infinity or negative infinity, this thing goes to 0, because you'd have a really large number in the denominator. So that's how we get y equal to 0 for our horizontal asymptote when the degree is smaller on the top. So let's say we have a degree of 2 on the top and a degree of 3 on the bottom, or something where it's n is smaller than m. Okay. If they're equal, let's look at let's make the degrees the same, and I'll do the same numbers in this case. I'll do 3x cubed over 5x cubed. Okay. And I'm just looking at the leading coefficients. I'm just looking at the ratio of these two, ignoring all the other stuff because we're kind of talking about end behavior. Okay. Now, notice what happens there. The x cubes cancel, and we just get 3/5. Okay. So this would be our horizontal asymptote for the case where the degrees are equal, right? 3 and 3 are the same, and we just get 3/5. That would be y equals, right? This would be y equals 0, right? Because we have, make x really large. Here we don't have x, right? So it goes away, and we get y equals 3/5. So when the degrees are the same on the top and the bottom, we just take a ratio of those two leading coefficients, a sub n over b sub n. Okay. If the degree is greater on the top, let's say we had this. Let's say we had 3x cubed over 5x squared. Okay. And if we reduce that, we get 3x over 5. Okay. Now, if you make x really big here, plus infinity or minus infinity, this thing goes to infinity. In other words, we don't have a horizontal asymptote. That as x gets really big, y gets really big, positive or negative. Okay, so here we don't have a horizontal asymptote when the degree is greater on the top than it is on the bottom. Okay, so basically we're just taking a ratio of those two leading terms and then simplifying. Okay. Canceling out our common x's, right? And then make x really big and see what happens. Here, when you make x really big, this goes to 0, right? Okay. Here, when you make x really big, it doesn't matter because you get 3/5. Here, when you make x really big, you get infinity, right? So here, in the first case, we have y equals 0. Second case, we have y equals 3 over 5. Third case, we don't have a horizontal asymptote. Okay, so let's look at an example here. Let's say we're trying to find the vertical and horizontal asymptotes of this rational function. Okay. 3x squared minus 2x minus 1 over 2x squared plus 3x minus 2. Okay, so first thing we do is factor. We factor the denominator, and we see this thing is 0 when x is a half, and this is 0 and x is minus 2. So those are our vertical asymptotes, where it's undefined. Okay, so we factor our denominator and see where it's equal to 0, and that gives us our vertical asymptotes. Graph can never exist there, right? And that's the ones we exclude for our domain. So our domain is x is not equal to 1/2, and x is not equal to minus 2. Okay, and then, so the vertical asymptotes are x equals 1/2 and x equals minus 2. Horizontal asymptote, the degrees of the numerator and denominator are the same, so that would just be 3/2, and that's our horizontal asymptote, is the line y equals 3/2. Okay, so we have a horizontal asymptote of y equals 1.5 or 3/2, and we have these vertical asymptotes. So that helps us, to start to construct our graph, right? Because we can put those dotted lines, these vertical dotted lines, in this horizontal dotted line, and those will be, help us define where our graph will go. Okay, so we're going to use these general guidelines for graphs of rational functions. So sketching graphs of rational functions. Start by factoring. Factor the top and the bottom. Okay, so that'd be our first step. Intercepts. Okay, intercepts is find the x-intercepts by setting y equal to 0. So that would just be the zeros of the numerator. Okay, so the only place where your rational function is 0 is where the numerator is 0. Remember, the denominator being 0 is where it's undefined. So that's the only place where we have x-intercepts, is where the numerator is 0. Okay, and then the y-intercept is we just set x equal to 0 and solve for y. Okay, remember we just said vertical asymptotes by turning the zeros of the denominator where it's undefined, right? Okay, and then see whether y approaches infinity or minus infinity on each side of each vertical asymptote by using test values. Okay, so it's either going to go y close to those vertical asymptotes, y is either going to be plus infinity, or y is going to approach minus infinity. We have to see which one it is. Okay, now the horizontal asymptote, we just described earlier how we can use those rules, but basically you're just taking the ratio of your leading coefficients, right? You take the first term, ratio of the leading terms, right? And then making x really large. Okay, so define our horizontal asymptotes. And then our last step is just sketch the graph. Graph the information provided by the first 4 steps. Plot as many additional points as needed to fill in the rest of the graph of the function. Now here you may have to plug in some points, okay, to see what it looks like, close to your asymptotes, and also to test points between intercepts like we did for our polynomial function. So there is some plotting of points involved. Okay, so let's start with this example. R of x equals 2x squared plus 7x minus 4 over x squared plus x minus 2. Okay, start by factoring numerator denominator. So this gets factored 2x minus 1 times x plus 4. Denominator is x minus 1 times x plus 2. Okay, so first of all, our x-intercepts is just where the top is 0, not the bottom, just the top. Okay, so x equals 1/2 is one intercept. That's where that's 0. X equals minus 4 is the other one. That's where this is 0. Okay, so we're only looking for x-intercepts, zeros of the function, right? Where y is 0 is where the numerator is 0, not where the denominator is 0. Okay, so just these two. Okay, so for our y-intercept, plug x equals 0. We can put it into our original form or our factored form, but if we do that, we're going to get, y is 2. R of 0 is y when x is 0. So we have 0, 2 as our y-intercept, right? That's easy to do. Okay, vertical asymptotes. Okay, that's where the denominator is 0. Okay, so that's where we have x equals 1, x equals minus 2. And we can see that our factored form of our rational function is this, right? So we're going to see where the denominator is 0. So that would be x equals 1 and x equals minus 2, where it's undefined. So that would be our vertical asymptotes. Okay, now we want to look at behavior near our vertical asymptotes. Okay, so we don't know if y goes to plus infinity or minus infinity on each side of the vertical asymptote. Okay, so we use test values. So we're going to look at x being close to 1 from the negative side. That means we're getting close to 1, but from the left. Okay, so 0.9, 0.99, things like that. Okay, so we're approaching 1, but we're approaching it from the left-hand side. Okay, so when we try 0.9, we can just look at the sign, so we can use our factored form, right? And just look at the sign, okay? So we don't even need to get the number, because we know it's either going to be plus infinity or minus infinity. So we plug in 0.9 for the factored form. We're going to get a positive times a positive, okay, divided by a negative times a positive. And all you have to do is add your negatives. And if you have an odd number, then your answer is negative. So we have one negative, our answer is negative. So this y is going to approach minus infinity. So we don't need to really get the number there. We just need to get the sign, like we did for our absolute value inequalities. Okay. So as y approaches, or as x approaches 1 from the negative side, from the right-hand side, then y approaches minus infinity, because we have that one negative. So there we can say, as x approaches 1 from the negative from the left-hand side, y approaches minus infinity. Okay. And then when we approach 1 from the positive side, let's say we're on the right-hand side of 1 and we go towards 1, so we look at like 1.1 or 1.01. If we plug that in, we're going to get all positives for the 4 factors. Okay. So our answer is positive. So that means that as x approaches 1 from the right-hand side, y approaches plus infinity. Okay. And then we do the same thing with negative 2, sorry. So as x approaches minus 2 from the negative, from the right-hand side, from the left-hand side, y approaches minus infinity. Okay. And as x approaches minus 2 from the right-hand side, because we have 3 negatives here, and as x approaches minus 2 from the right-hand side, so here we might be looking at something like 1.9 in these factors. Okay. Let me restate that. Since we're approaching minus 2 from the negative side, here we might be looking at something like minus 2.1. Okay. So here, let me write down what the x's. We try as x's, to see. So here we would say like x equals minus 2.1. That would be to the left of minus 2. Here we could use like minus 1.9. That would be to the right of minus 2. Okay. Here we already did these, but we could say x equals 0.9. Okay. And then here we could use like x equals 1.1, and that's the example we already looked at. But in the minus 2 case, if we approach minus 2 from the negative side, we can use like minus 2.1, and that gives us a negative times a positive over a negative times a negative, and we plug in minus 2.1. Okay, which gives us a negative, right? Because we have 3 negatives, 1, 2, 3, odd number. Okay, so y approaches minus infinity. Okay, we use something like minus 1.9. and plug them in here, the factors. We're going to get a negative, positive, negative, positive, which has 2 negatives, so our answer is positive. So y approaches plus infinity. And we already did these two for 1, right? Okay, so now let's look at our horizontal asymptote. Since the degrees of the numerator and the denominator are the same, we can just take the ratio of the leading coefficients. So the leading coefficient of the numerator is 2, leading coefficient of the denominator is 1, 2 over 1 is 2, so our horizontal asymptote is the line y equals 2. Okay. Now if you forget that, you can just take the rule, about checking the degrees, just take the ratio of the leading terms. Okay. And we're going to say y approaches that. Okay. Now, when we have 2x squared over x squared, notice those x squared just cancel and we get 2, right? So we could say y approaches 2 as x approaches plus or minus infinity. Okay, and that's our end behavior, right? So if you think end behavior when you talk about horizontal asymptotes, okay, and just take the ratio of your leading terms and make x really big, right? Because x is going to plus or minus infinity, and see what happens. Well, here x just cancels, right? So we get y equals 2, and we actually have a horizontal asymptote of y equals 2. Okay, now we put all this information together to get a sketch of the graph. Okay, so there's our y-intercept, right? We had our x-intercept here, okay? And we know that, let's look at our vertical asymptotes. Remember we did as x approaches minus 2 from the negative side, y approaches minus infinity, so that's going down. And then as x approaches minus 2 from the positive side, y approaches positive infinity, so it's going up like this. So that's how we get those two from looking at our behavior near our vertical asymptotes. And then the first one we did was when x equals 1, right? So when x equals 1 approaches 1 from the negative side, 0.9, our y approaches minus infinity. And when x approaches 1 from the positive side, like 1.1, our y goes to positive infinity. So that's how we get those parts of the vertical asymptote. Okay, so we had that. We had the y-intercept, right? And we have these 4 parts. Okay. Now the rest is end behavior, right? So the end behavior is, remember we said, as x approaches plus infinity, y approaches 2, it's going to have to go like this, right? It's going to go down towards it. And then as x approaches minus infinity, y approaches 2. So we're going up to 2 as y approaches y is going up to 2 as x approaches minus infinity. And we can verify this by checking some points, but we had these intercepts, right? We had minus 1, 2, 3, minus 4, right, for an intercept, and we had what did we have? We had 2 for a y-intercept, right? Okay. So domain and range, remember domain is x, set of all x, such that x is not equal to 1 and x is not equal to minus 2. Those are our vertical asymptotes. Minus x equals 1, x equals minus 2, excluded. Okay, and then the range is going to be, now here, check the range here. Notice we have this horizontal asymptote, but it's defined there. The function crosses it, and it can do that. Think about what's happening with our y. As we go up the y-axis, this function always exists because of this middle curve, right? There is no gap as far as y is concerned. So our domain, or our range, is going to be all reals. Okay. And here's some points we plugged in, kind of to fill in the gaps. You know, look at x at minus 6, minus 3, minus 1 to kind of get the rest of the information. Okay. And then look at some positive values of x to get your y's too, to see what's happening there. Okay, especially in between here, you want to see what it looks like as you get in the graphs, this kind of middle part of the graph to see what it looks like. Okay, that's all we're going to do for this section in the video lecture. We're not going to look at slant asymptotes in this section, so don't worry about that. So our asymptotes are going to be vertical or horizontal only. Okay, I will do some more examples in class so you get a better idea, but we're pretty methodical about this, about following these steps and looking at our asymptotes, our intercepts, end behavior, etc., and then plotting points to figure out the rest.